Hello everyone, today we're going to be going through a synchronous up counter, and I may be doing a slightly different process to what is in the module, the EE1629 module, but this I think is an easier way to look at it. So with an up counter, obviously with a 2-bit, we're going to find that we want a sequence that looks like this, and then it loops around. So the way we're going to, first of all, what we're going to do is we're going to name them as different states. Some people call these state machines, but basically we're manipulating a state machine to be an up counter. So we have 0, 0, 0, 1, 1, 0, 1, 1. And the best thing to do is to draw a state diagram, and this is important for state machines because they don't just count like this and then go back to the beginning. You could say you just wanted to count between these two. You draw a state diagram which would look like this. If you just wanted to count between those two, you would do like that. And then which is useful for some applications because you can manipulate a synchronous D-type circuit to get whatever output you want in a sequence with a sequence generator. So let's just draw the state diagram. So now we have the state diagram. Now let's just draw our circuit before we've done any sort of calculations. And when I say calculations, I mean we're going to calculate the logic in a minute to make it so that this circuit does what we ask it to. And we're going to be using D-type flip-flops. So since it's a synchronous circuit, the clocks will be connected together. It's also known as a common clock because they're common to each other. Now we have our outputs Q1 and Q2. So now we have our basic circuit, and you can see we haven't connected anything to D yet. That's because we haven't calculated what we want feeding into D. And the way we do this is to draw a table. So I'm going to draw a table with 3 columns: state, state number, current state, and next state. And current state is going to be Q2 and Q1, and next state is going to be D2 and D1. So we're going to have 0, 1, 2, 3 and 4. Wait, no, not 0, sorry. Well, actually, I've made a small error here. What you would normally start from 0. So we're just going to start from 0 like that, which ruins my little diagram. So I'm just going to redraw that. Okay, 0, 1, 2, and 3. So state 0 is going to be 0, 0. And we want state 0 to feed to state 1. I'm just going to draw all of these, because this is what the state number is, so, and this is what's the value associated with that, or the output we want from that. Our next state, since we just want them to jump between these like that, because we've drawn a diagram like this, state 0 is going to go to state 1, so 0, 0 is going to become 0, 1, so we're going to draw 0, 1 there, and 0, 1 is going to become 1, 0, 1, 0 is going to become 1, 1, and 1, 1 wants to become 0, 0. Now, we are going to find out the logic for D0, D2 and D1. And the way you do that, it's just a simple truth table. If you just ignore D1 for a moment, D2 is 1 when Q and when Q1 XOR Q2. You can see this is an XOR. So we can write that logic as D2 equals Q1 XOR Q2. Now let's do D1. So D1 equals, and then let's have a look at this. You can see it's 1 when Q1 and Q2 are NOR together, or when Q2 equals 1. So we could draw a Carnot map for that, or we could just do it by observation. So it's going to be not Q1, because you can see there's common zeros. You can do it any way you like, figure out the logic, but it's very basic. It's just combinational logic, and doesn't matter what Q2 is, so it's just going to be not Q1. So this is not Q1, so now we have our logic, our Boolean logic. We can draw that on the circuit. So D2 is going to be XOR Q1 and Q2. So let's just draw an XOR gate here. Apologies for my bad drawing. But, it's going to be Q1, so we're going to connect it to Q1. And Q2, XOR Q2, and that feeds into D2. And since D1 is Q1, not Q1, we could go from Q1 and then draw a NOT gate, but there's no need because we have Q bar here, which is the same thing. So that's our circuit. And a 3-bit one is more complicated, a 4-bit one's more complicated, but if you just work through it methodically, then you'll be able to come to you can simplify the logic using Boolean algebra. This is already its basic form, or canonical form really, so it's not too much of a problem. But if you say you had like Q1 plus Q2 and Q1, or something like that, and then plus, and then just like a bunch of logic. Then you want to simplify it so you don't use as many gates. But I'm going to leave this here, and I'm going to go on to state diagrams, or like this, but a bit more. I'm going to elaborate further on it in my next video with state machines. So I'll see you then. Any questions, put them in the comments, and if you want, you can like the video, that would help. Okay, see ya.